Hi everybody, welcome to another video in Calculus 3. We go to a new chapter, chapter 16, multiple integration. So in this chapter, we'll study about integrals of multivariable. So let's just compare what we did in Calc 1 and what we'll do now in Calc 3. Derivative for single variable, we just have dy over dx and derivative, and integral, just that because it is Calc 1. Now, what we do now is a multivariable calculus. Have a function of two or more variable. It could be more than that. Then with derivative, we have the partial derivative. Notation is either this or this. And now we go to a double integral. Since we have two variables, there will be two. And usually we will, instead of write like this, we will write dA here could be dy or dx or dx or dy. Let's just say dy dx, something like this. And the difference in here is that we only have definite integral, meaning that it has to have the limit. Let's say just go from a to b, c to d, something like that. So have to be the limit, have to have limit. In Calc 1 we might have indefinite integral where we just don't have the limits. Now this has to have the limit in order to do it. Alright, we go to that part in a minute. Alright, and also in Calc 1, what this one calculate is it is equal to the area. If it is above the x-axis, let's just assume it is above the x-axis, it will calculate the area from A to B, the area under the curve. That one equal to the area of this part. So area under the curve for one dimension. Now for one variable, area under the curve for one variable. Now we go to two variable. The area becomes a volume under a surface. So area under the curve, volume under the surface, kind of we just increase one dimension to it. So apparently, as mentioned before, we only deal with definite integral for multiple integral. Right. Volume below the surface. So we have the surface of the function of two variable look like this, and if we want to find area of a curve, or in this case it's not flat surface, what we do is we just divide into a square, take a little square on the xy plane, and then we have the height, and with that we construct kind of a rectangular box, and adding the volumes of all of those boxes give us the estimated volume of the volume under the surface. Just like we divide this into a bunch of rectangles and we estimate the area. That's the same thing, that's the Riemann sum. Now we do the same thing, but we will have the area on xy plane, and then we find the height. So this is the height times the base area, so we just have the volume. So we can calculate that way by estimate the volume of, add the volumes of all of those rectangular boxes. Right. If you did not bring this out, the only thing you need to know, the only thing you need to write down for the whole page here is this. In order to do the double integral, in this case they're called the double integral. In order to do that, it is evaluated by first evaluate the inner integral with respect to one variable when holding the other variable fixed. So evaluate the inner integral by holding the other variable fixed. Then we evaluate the outer integral. So just integrate the inside, and then what we have from the inside, integral from the outside. We can only do one at a time. Whatever the variable we integrate, the other variables will be treated as a constant. So just like derivative, partial derivative with respect to x, for example, then y and z and everything else I consider constant. Right. let's evaluate this. Evaluate volume of this, and h of x is given by this. So if we put them together, we can write this as v from 0 to 1 dx. That is the outside, and the inside is h of x, which is another integral. Right. So we have an integral inside an integral. So we do inside out from here, do first, then on the outside. Yeah. But this one we've written like that, so we don't have to confuse. Anyway, I'm going to evaluate this first. Right. Go from 0 to 2, 6 minus 2x minus y dy. Notice that the difference between the different derivatives and integral is that here we have the partial derivative. Here we don't have the partial integral. We still have just have dy of dx. We don't have like that. Right. Yeah, we don't write the curly d, just regular differential. Anyway, so we integrate. Now this one with respect to y, we will treat everything else as constant. Of course, that including the constant itself, 6. So we integrate 6 integral of constant with respect to y. We stick the y to it. Next, 2x is a constant with respect to y. Integral of that is 2x times y. And finally, integral of negative y. Integral of y is y squared over 2. So we integrate with respect to y. Everything else is treated as constant. And also here we have y, so we have y equal to, so those will be the limit for y. If it's clear, we do not need to write y equal to, but if we want to be absolutely sure, yeah, just write y equal to 0 to y equal to 2. Right, now put 2 in it, put 0 in it. So we have 6 times 2, put 2 in for y, minus 2x, 2 in for y, 2 in for y. Now we subtract, we put 0 in for y. Yeah, so this is just fundamental theorem calculus. So in terms of integral, we will not have anything new here. Just integrate like we normally do. Right. So 0, 0, 0, all of them gone. And we just have here 12 minus 4x. And that is 4 over 2 minus 2, which is equal to 10 minus 4x. So h of x is equal to that. Now let's go back to v is 0 to 1 h of x dx. And we just substitute this is h of x into this. Right. And then we integrate with respect to x constant. We stick an x to it. For x squared over 2. That go from 0 to 1. So this gives us 10x. 4 and 2 cancel out. 2x squared. 0 to 1. Put 1 in for x. And put 0 in for x. This goes to 0. And this is 10 minus 2 is 8. Usually if it is just a polynomial with the rational limits, the answer is going to be rational. So I'm just going to use a calculator if you want to. So integrate 10 minus 4x. Don't forget to specify the variable. Yeah, so simple enough. So integrate inside and then outside. When we integrate with respect to y, we keep everything else as constant. With respect to x, we keep everything else as constant. Right. Now, moving on then. Double integrals on rectangular regions. So what we have here is called the rectangular regions. A is between two constants and y is between two constants. So if we define that, does that matter if we use dy dx or dx dy? And the answer is no. According to Frobenius theorem, if the limits all of them are constant, it could be dx dy or dy dx. It doesn't matter. What it matters, the only matter is make sure when if you put the dy on the outside, that is the limit for y. And if we put the dx inside, that'll be the limit inside. If we move outside, the x will be goes outside. So make sure you put the limit accordingly. Outside with outside, inside with inside. Do not switch the limit. It just say that we can switch the order, dx dy, but the limit have to follow. We cannot change that. And most importantly, those must be constant. If one of them are not constant, we cannot do this. Right. Now, just to show that it works, I just do one example here. Let's find the volume of a solid bounded by the surface over the region. This is the region. Use both possible orders of integration. Now I'm going to use dx dy first, and then I'm going to do dy dx. Alright, so let's say the integral I equal to, let's put dx dy. Right. Okay, this one, dx dy, so dy on the outside, and y limit from 0 to 2. So be careful, I write this, 0, y equal to 2. And that is dy on the outside. If you want to even more sure of it, I will put you can put parentheses here and say inside the integral. It's another integral. We want dx dy, so we're going to put dx inside, and x goes from -1 to 1. The function, we want the volume below the surface, so we're going to put just that function. Right, we'll just integrate inside then outside. So the limit for x, that's correct. Limit for y, that's correct. The function in the middle. Right, just do inside first and then outside. If you're sure about the limit, we just drop y equal to, we just say from 0 to 2. We don't need to, if it is clear to the context. Now integral with respect to x from the inside. With respect to x, y is a constant. Right? So integral 4 is a constant. It's going to be 4 times that constant. And then 9. Integral of x squared is x cubed over 3. We still have y squared, a constant. So we integrated the inside, but we need to take care of the limit, -1 to 1. Right. Once we do that, we can do integral with respect to y. Right. I'm going to put 1 in for x. 4 times 1. 9 and 3 cancel out. That 3. 1. Sorry. Yeah, I should check to see what I wrote. Yeah, 9 3 cancel out. That's 3 1 cube. Y, we don't know what y is, but it's a constant. And then we subtract where we put -1 into it. 4 -1 3 -1 cube y square. Yeah, put 1 in and then put -1 in. And then we have, whenever we're done with that, evaluate with respect to y. Right, let's simplify inside. Right, we have 4, that's 1 minus -4, so 4 minus -4, so 4 plus 4, so that gives us 8. Right, and this is 3y squared minus -3y squared. 3y squared minus 3y squared, that's plus 6y squared dy. Right, so do inside first and then outside. Once again, this is a polynomial. Limits are rational number, so I just use a calculator. So a lot of time here. And also, step y, we can just use x. That's 32. So that is, we integrate using dx, dy. Now we do the same thing using dy, dx. Right. Now we do dy, dx. So we put dx on the outside, and on the outside, x is between -1 and 1. And then we just put the parentheses here. Yeah, so we keep the dx on the outside. The inside is y. Integral for y go from 0 to 2. And we have the function. So in this case, we do dy dx. Right. Now we just integrate from the inside. Outside, we just have -1 to 1 for x. Right, integral. 4 with respect to y is 4y. And 9x squared is constant. Stay there, but for y squared, integral y squared is y cubed over 3. Yeah. Limit y go from 0 to 2. We just say from 0 to 2 if it is clear to the context. Now we evaluate. Put in 2. Nine, 3 cancel out. That 3x squared y cubed and y equal to 2. So we have 3x squared. Put 2 in, 2 cubed. Now we're going to put in 0 for y. Yeah, when we're done inside, just integral respect to the x. Right. And this 0 is gone. So we have -1 to 1. 8, 8. And this is 2 cubed is 8 times 3, 24 x squared dx. Right, let's integrate from -1 to 1, 8 plus 24 x squared dx. Yes, that's also 32. Yeah. So it's not a proof for the Forbidden theorem, but at least it's this example confirmed that that's how the Forbidden theorem actually works. So once again, two things need to happen. The constant limit, all the limit have to be constant. If one of them is not constant, we cannot do that. In the next section, we more focus on that. Focus on the case where the limits are not constant. But in this section, all the limits are constant. If the limit are constant, meaning we can do dx or dy by dx. But whenever we put dy and dx, make sure that the limit must match. So like if we put for x is between -1 and 1, so make sure the limit for that. And when for y, limit from 0 and 2, make sure we write that for dy. Right. Now, those are two things for the Forbidden theorem. Now we can take this to another level if the functions are separable. So I'm going to write this. If constant are limits, I should say if limits are constant, sorry, backward. So we know how the limits are constant, and the function is separable. Then I'm going to write like this. So let's say we have the limit from a to b. A to b is for x, and inside we have c to d, and the function is separable. So the function separable, meaning that the function is equal to a function of x and the function of y. So we separate the function in terms of the product. So I'm going to write g of x and h of y. So the y, c and d are limit for y, and a and b are limit for x. So limit are constant and the limit are matching. That Forbidden theorem. Now take this to a whole new level when we say if the function is separable, meaning if this function can be separated as a function of x times a function of y, we could put all the x's together. Do that first. And then we just have the integral. So group all the x together and group all the y together. And that's the product of two integrals. So this only if the constant limits and the function is separable. So we can separate as a function of x times a function of y. In this case, we just do each one of them. That should be easy. Yeah. So use this as much as possible. Every time we see the function are separable, go ahead and do that. Save you a lot of time. Right. Let's look at the first example. evaluate this, and the limits are constant. This is good. We might be able to use this. So let's just write this properly. For x is from 1 to 2. The function, and then for y, for y is 0 to pi over 2. The function, I'm going to use different, let's use this, x squared sine y. Right. 0 to pi over 2 inside, remember inside out, not from left to right, inside out. So the inside is 0 to pi over 2, that is for dy. And the x is from 1 to 2, that is dx. Right. So, of course, if we switch the dx, dy, the limit will interchange as well. But, right, inside and out. Now, according to the Forbidden theorem, this function, if we can just write the x or dy, but even better if the function is separable. So we write this as a function of x times a function of y. In that case, we group all the x together, limit from 1 to 2, and we have the function of x. And then the integral of y with the function of y. Only do this if the functions are separable. We cannot do this if there's a y in here and there's a y x in here. We cannot do that. But if it works, that's very nice. And each one of them we can just use a calculator. Right, from 1 to 2. This should be easy, but don't have a lot of space. And notice that if we have a polynomial and the limit are rational, the answer is always rational, meaning we can always be able to put it as a fraction. So we have 7 over 3. And then from 0 to pi over 2, if we use this, make sure it's in the radian mode. Integral of sine is negative cosine. You can do that by hand too. It doesn't matter the variable. We can put x or y. Doesn't really matter. So the answer is 7 over 3. Yeah, this we use a calculator. But the idea here is if the function is separable, the limit is constant. Just group all the x together, all the y together, and do 2 integrals. That's will be easy. Right. Next, can we still do the same thing for this function? First, 0 to 1 is for x, and 0 to 2 is for y. The inside function a to x plus 2y. Right, inside 0 to 2, so that is the inside is dy. I said if you want to, you can just put the parentheses around it. And then on the outside 0 to 1, which is for x, so dx. Right, so of course you can do dx, dy, dx, doesn't matter. But is this function separable? Right. So remember these properties. A product of two things with the same base, b to the m plus n. right? So now I can write e to the x plus 2y is e to the x times e to the 2y. So when we write like that, a product of x times a product of y, so indeed it is separable, right? Inside 0 to 2, which is dy, outside 0 and 1, which is dx. Right, now group all the x together and all the y together. So the 1 for the x and the function for the x is e to the x. Then for y, limits from 0 to 2, and the function is e to the 2y. Right, if we do this by hand, we won't be able to get a nice answer because this is irrational answer. Yeah, it's not going to be, should be 1, not 7, sorry. But still, the answer is not going to be anything nice and even. Now, so we have to do this by hand. Luckily, this is e to the x, so that's relatively easy. Integral of e to the x is still e to the x, going from 0 to 1. And e to 2y is 1/2. E to the 2y go from 0 to 2. Right, put 1 for x, put 0 for x. Put 2 in for y. And put 0 in for y when we subtract. E to 0 power is 1. So we'll have e minus 1 times 1/2 e to the 4th minus 1/2 e to 0 power, which is 1. And now multiply it out. 1/2 e times e to the 4th minus 1/2 e minus 1/2 e to the 4th minus the plus, that's 1/2. Minus is negative. Negative is positive. Right, so we have e to the 1st times e to the 4th is e to the 5th minus 1/2 e minus 1/2 e to the 4th plus 1/2. Yeah, so that's why the answer is not anything rational. But again, if the functions are separable, the constant and the limits are constant, then just group all the x together and all the y together. Right. Now things get more complicated. Choose the more convenient order to integrate, then evaluate. So this one is a little bit of work. Right. Let me ask you this first. If you have a function exactly like that, and as you find derivative with respect to x and then derivative with respect to y, because that's easy, but my question is, which one is easier to do? I hope your answer is, if we take derivative with respect to x, there's only one x here, all the y are constant, so this is easier to do because only one x. As opposed to here, there is a product. Y show up in each of the factor, so we have to use the product rule here because y show up two different places in each of the product. So we use the product rule, and that is a lot more work than this, right? So that is derivative, integral, kind of same way. When we look at this, y show up in two different places. Yeah, so if we put dy inside, this is going to be an integration by parts. But if we put the dx inside, it is a regular substitution. So on this one, it will be a lot better if we use dx dy, because dy dx we have to handle integration by parts. Right, so as mentioned before, we do dx first and then dy, because only one x and there's two y show up in two different places in the product. That's how complicated. So do x first and then y, and inside and outside. So the inside from 0 to 1, and that is for the x. The function y e to the xy. So that is the inside. The outside, by the way, when we write like this and we don't know which one which, we're just going to put dA. But if you want to be specific, we put dx dy or dx times dy or dy times dx, and then inside with the inside limit, outside with the outside limit. Right, let's integrate. I'll keep the limit outside. And the inside limit, inside integral y e to the xy dx. Now, just need to integrate. Notice y is a constant, right? So keep that in mind. So we integrate just my little note, make sure that I don't forget what I need to mention. Right, 0 to ln of 2. Right, integral of e to the xy, if y is constant. So this is exactly, I've asked you what is the integral of something like, what's the integral of kx? If k is constant, then I'll say it's e to the kx over k plus c, right? Same thing here. So this is e to the xy over that constant. So k, instead of k, we have y here, right? Or if not, we can just use the substitution, and let's use substitution. Right, I'm going to let xy be u, or u equal to xy. Then I can take derivative. Now with respect to x, right? With respect to x, y is a constant. Even though I write like this, but that should be partial derivative. But still, with respect to x, it's going to be y. Multiply the dx. And so for the x, du y. And we substitute this in for dx. Right, so that integral, I will not do anything. I just substitute in what we have here. Okay. I just continue here. Right. So the integral is from 0 to 1. We should change the limit too, but a bit complicated. So I'm just going to keep 0 and 1 here for a moment. Y, e, xy is going to be u. So this is just standard substitution problem, and dx is du over y. Du over y. And then we have dy. So the inner integral becomes this. Just to be clear though, we haven't changed the limit, did we? So the limit is x equal to 0, x equal to 1. So it's still x, we haven't write that in terms of u yet. right? Y and Y cancel out. And then inside we just have the limit is for x though, not for u. But the integral in terms of u. And then next, where's the ln? E to the u is just e to the u. But notice that this is the limit from x, not for u. So if we want x, make sure that we have to write that in terms of x before we substitute in the number. Otherwise, it will be terrible. Integral from 0 to ln of 2. Now u is xy, right? Right. Put 1 for x, put 0 for x. So that's the limit for x. If we do the substitution, make sure we have to go back to the variable. On this one, I don't want to change the limit because the limit usually a bit complicated. And yeah, of course you can change the limit too. It doesn't matter. But here, make sure that the limit here is for x, and we only put in for x. Don't put in for u. Put 1 in for x. So I have e to the 1 times y. And then e to the x is 0 times y dy. So this gives us e to the y. E to 0 power is 1. And we integrate. That should be easy, right? E to the y minus y from 0 to ln of 2. Put in ln of 2 in for y. And then put in 0. E and ln of 2 cancel out, so that is 2 minus ln of 2 and minus 1. That's 0, so 2 minus 1 is 1, so we have negative ln of 2. 2 minus 1 is 1. So that's what we have. So that's simple enough, right? If we do this with the dx, with the dy, then dx, inside we have to do integration by parts, and that could be complicated. So if we have a choice between dx and dy, just choose the one which is more convenient. Right. Next, kind of the same thing. Y show up two different places. And that is product. So probably we could be wise if we put dx in the inside. Do that first, and we take care of the others. Right, so the x from the inside, x go from 0 to 1. The function for now, this is y cubed. And also the reason that this one we do not do like we did before with the separable function. Yeah, where was that? Oh. We didn't split the function because this function we can split This e to the xy, yeah, cannot split that. Same thing here, sine of xy square, cannot split that. So if the function is not separable, we just have to do it. We cannot split that into two integrals. So the x go from 0 to 1, and we have y cubed sine xy square. So that inside. On the outside, limit for y go from 0 to square root of pi over 2. That is dy. Right. I choose dx inside because there's only one x. If you do that with iteration, that iteration by parts. Right. Now, this is substitution. Once again, I'm going to let u equal to this. Let u equal to xy square. We're going to solve for the x. So we're going to take derivative with respect to x. Once again, I'm just going to use that integral. I mean, not partial derivative, that notation. Derivative with respect to x, y square is constant. Derivative with respect to x, just y square. Right? Move the dx over du equal to y square dx. So dx is du over y square. So I can substitute that in for dx. And just like the last problem, just be clear that this one equal to an integral I, which continue is that. Now this one equal to integral I, which continue is that. Because that part is just like the scratch work. Right from 0 to 1, we still have, again, I don't change the limit here because that look complicated. Our limit is for x equal to 0 to x equal to 1. Just be clear about that. This is not limit for u. Right, y cube stay there. Sine, instead of xy square, that will be u. Right. And then dx is du over y square. That is inside. Then there's dy. Right. Y square, y cube cancels. That should be a y left. I'm still writing the integral 0 to 1. There's a y sine u du. Once again, this is limit for x. And then dy. Fine. Actually, y is a constant with respect to u, or with respect to x. So we can just take the x, the u, the constant outside. Constant will be on the outside. Integral of sine u is negative cosine u, right? Notice that the limit is for x equal to 0, x equal to 1. Once we done that, there's a dy. Right. Let's substitute u back into xy square. Actually, it's negative cosine of xy square, where x equal to 0, when x equal to 1. and this is dy. Right. Yeah, that integral. I just reshuffle and then now substitute for 1 in for x, substitute 0 for x. Negative y cosine x equal to 1. And then subtract when we substitute in 0. In for x, not 0 for y. And then we have cosine of 0 times y square. Yeah, just put 0 for x and then 1 for x and subtract them. So this is fundamental theorem of calculus. Just substitute into this x, and that's what we have here. Right. Cosine of 0 is 1. And that is cosine y squared. So we'll rewrite this as 0 to square pi over 2 minus y cosine of y squared minus a negative, so that's a plus cosine point, so that's just plus y. Right, now we split because we can integrate that. Now this one's easy, polynomial. This one I will use substitution. Let u be, actually we can still use u because we're done with u here. Let's do that again. Oh, v, doesn't matter, I'll use v then. Let's v be this, and we solve for dy. So let v be y squared. So derivative of v with respect to y. We need to do that so we can solve for y. It's 2y. So dv is 2y dy, and dy is dv over 2y. And I substitute that in here. Right. I should mention that on this one you should write very small. And once again, this is the limit for y. So I don't change the limit here yet. No, I don't change the limit at all. I just go back to y later. Right, negative y, stay there. Cosine. Instead of y squared, I can use v. And instead of dy, I'm going to use dv over 2y. So that is this integral. The other integral I just integrate easily. That's y squared over 2. I'll go from 0 to square pi over 2. Yeah. Just cancel the y. And that's negative. The 2 from the bottom. So bring on the outside. That's negative 1/2. Integral y equal to 0 to y equals square root of pi over 2. And we have cosine of v dv. Right, and that gives us plus 1/2 y squared 0 to square pi over 2. Once again, sorry about this. just continue on this page. Right. So we have negative 1/2. Integral cosine v is sine v. But note that these limits are for y. Of course, we can change the limit too. Here, yv equal to y squared, so the limit can change from 0 to pi over 2. Yeah, I can do that too. Plus 1/2. 1/2. I'm going to substitute in square root of pi over 2 square, and then substitute in 0. Yeah. So that's for the second integral. Sine v, v is y squared. That's one gone. That one is 1/2. Square cancel square root. So we have that. And then substitute in the limit. Negative 1/2 sine square root of pi over 2 square. Minus negative 1/2 sine of 0 square, and plus pi over 4. That one. Right. Sine of 0 is 0, so this one gone. So we have negative 1/2 sine of square pi over 2 square cancel square root, plus pi over 4, and sine pi over 2 is 1, so we have negative 1/2 plus pi over 4. Right. If you think that this one is complicated, wait until you see that if we do that in the other way. Right. So once again, this one we do it in the order of dx dy because there's only one x here. So we just have two substitution. If we do the other way around, that will be integration by parts. In fact, I'm going to do that now too. Right. Anyway, so that's what we have. I should give you a heads up on this is a long problem. Right. So that certainly works. Now, let's try this one. If we do it in the dy dx order, see how bad it can it be. Right. So I'm going to switch the dx on the outside, 0 to 1 on the dx, and go from 0 to square pi over 2 dy in the inside. The function y cubed sine of xy squared. Yeah, actually, this one I will change the limit. It doesn't really matter. Right. You can use u, you can use v, but since we have y's here and then y's here, more likely we're going to have an integration by parts. So let's write down, right, the two functions here. So more likely we're going to use integration by parts. Integration by parts. Integral of u dv is uv minus integral of v du. Right. So we're going to use that because there's a function, trig function, and then that polynomial. Right. So we still need to use substitution. The reason I write this one first, so in the substitution we might use some other variables. let's say W, because I don't want to use U and V here. So I'm going to let this be W. And I'm going to solve for dy. In order to have dy, we will take derivative with respect to y. Derivative with respect to y, x is constant. Derivative of y squared is 2y. Right. Move the dy over. And then we can solve for the w, solve for dy. So dy equal to dw over 2xy. Right. This, we go back to this. Now let's change the limits. Yeah, it's not going to be pretty. Right, w is equal to xy, right? We'll change the limit. Originally, the limit is for y equal to 0 to y equal to square pi over 2. And then w is equal to xy squared. So if we solve for w, w equal to x 0 squared, so that's 0. Now w equal to x square root of pi over 2 square. So that's pi over 2, so we have pi x over 2. So that will be the limit. So there's x in it. So I will substitute into the integral. On the outside, 0 to 1 is still limit for x. Of the inside, let's just write first y cubed. That's good. Sine xy squared. Xy squared is w. Dy w dw over 2xy. Now we write as the dw. The variable is in terms of w, which go instead of 0 to square pi over 2, we go from 0 to pi x over 2. Yeah, so we change the limit if we want to. The reason I didn't want to change the limit earlier, because in that case there might be an x and y in it. I still just want to keep the limit constant. That's all. But if you want to change the limit, yeah, that's how we change the limit. Still works, right? Right. Cancel something. Oh, by the way, there's dx on the back. There's something to cancel. There's a y here. Cancel with that, give us y squared left. Right. Integral w equal to 0 to w equal to pi x over 2. We have y squared sine of w, and then we have 2x. At the bottom is constant. We can even bring it outside here if we want to, but I'm just going to put 2x here. Then dw, then dx on the back. Now with this thing, this w is a variable, x is a constant. So we can certainly move the 2x on the outside. However, the problem is still y squared. Everything must be in terms of w, or maybe x, cannot be y. So we still have to go back and take care of it. Take care of it in this manner. W is equal to x y squared, right? So in that case, we can solve for y squared is w over x. So I'm going to substitute this in for y squared, because the answer now is the variable is either w or x, it cannot be y. 0 to 1. Yeah, we haven't do any integration yet, but just on the substitution. At this point, you can say this is a lot more complicated than the other one, and I would agree. And then sine of w, then 1 over 2x, and then dw dx. Right. Now on the constant, 2x and x, those are constant. I can take it outside. Become 2x squared from the bottom. W equal to 0 and w equal to pi x over 2. And we take those out. W is still the variable. We cannot take the w outside. With respect to w, x is a constant. We can take it outside. W is variable. Keep it inside. It's certainly doable though. It's just integration by parts, which is that one. So I'm going to do this integration by parts. Right, u is equal to something easy to differentiate. So u equal to w. So du is dw. And then dv. So it needs to find u and dv. dv is equal to sine w dv w. So to get back to v, we integrate. Integral of sine is negative cosine. Cosine of w. And go back to this integral. And like I said, you should not see anything this complicated, because the idea here is just how to set up the integral, how to integrate. We should not see anything this complicated, because it's way too advanced. Right, this is on the outside in the integral of x. So I'm going to write this in this outside integral. Right. Inside this integral is integration by parts given by that integral. So it's going to be uv, u, and v, u, and v, minus v integral of v du, integral of v, this is v, and du is dw. This integral evaluates from w equal to 0 to w equal to pi x over 2 dx. Right, let's simplify the inside. Right, won't be able to finish this problem, but at least I need to get to some certain step here. Right. Notice that here we change the limit for w already. Won't need to go back and substitute back in terms of x and y. We don't have to go back because here we change the limit. That's an advantage of changing the limit. We don't need to go back to the old variable. So we have the limit for w here, right? Just substitute in for w. We didn't do that earlier. So when we have this and we end up with this, we cannot put 1 in for u. We have to go back to x first before we can substitute. So there's a drawback in the substitution, whether we change the limit or not. All right. By the way, you don't have to write this down on the note. I just want to show that is how complicated this is. Integral negative negative, that's a plus. Integral cosine is sine. Right, one more step and then I'll stop on this problem. The integral on the outside, 1 over 2x squared. Right, now substitute pi x over 2 for w, for cosine pi x over 2. We cannot do anything with this. And then plus sine pi x over 2. That's where we put in pi x over 2. Now put in 0. 0 cosine of 0 plus sine of 0 . Right, this clear out somewhat. 1 over 2x squared. Now in terms of x, we should be able to integrate. Oh, we should not, but anyway, 0, because 0 times anything, and then sine 0, that's also 0. So this will just have negative pi x over 2 cosine of pi x over 2 plus sine of pi x over 2. If I multiply out the 1/2 x squared into this, I will have negative 1 over 4x squared. Oh, by the way, when you multiply, the x and the x squared cancel out. You'll just have pi on the top, right? Negative pi on the top, x and x squared cancel out, so that's just 4x at the bottom. And then we have cosine of pi x over 2. And then minus, oh sorry, plus 1 over 2x squared sine pi x. Right, I'm going to stop here because hopefully you know already. If we have an integral like cosine of something like this, nobody can integrate this integral. In fact, that defines it to be some order function. In terms of the function that we have, we cannot integrate this. So that's why we cannot integrate this separately. In order to integrate this, what we're going to have to consider, sorry, I forgot the 2. What we have to rewrite this as a product rule. And so we just integrate up something as a product rule. Integral cancel the square root, integral cancel the derivative. So we have to write this as a product rule, then we can integrate that way. We cannot integrate separate terms. We have to treat that the whole thing as a product rule, then we can integrate. I'm not going to do that because we do a lot more than we should in this problem anyway. So the point here is, if it's possible, we choose the dx or dy, dx, whichever is more convenient. And when I look at this problem, I say, oh, there's only one x and there's 2 y. Maybe just do dx first. Then I don't have to deal with iteration by parts. Right. Otherwise, that's complicated. And the last thing I want to mention, comment on this, is whether do change the limit or not. Just make sure that when we integrate, when we substitute back in, it has to be the correct variable to substitute in. If you don't change the limit, when we substitute in, it has to substitute in the same variable. If we change the limit, like what we do here, when we substitute in, we can just substitute into the limit. let's make sure just be consistent with the limits. Right. Don't worry about this. On the test, this is probably the most complicated integral you can have. Just substitution. Integration by parts is rarely you should not even see integration by part on the test. I'm not sure, you may, but it's very rare that the problem that complicated. Right. More samples. Let's look at this one. Right. Should we do dx or should we do dy? In fact, it doesn't matter here, because if we see this function you can just write this as the product of the function of x and the product of the function of y. So yes, the function is separable. So in that case, group all the x together, all the y together, and integral will be a lot more doable. By the way, this is a bit tricky. Right. By default, usually I prefer to put the dy in the inside, because after we integrate, we have x and then x on the outside, like we normally see. Right, the function I'm going to write as the product of a function of x and the product of a function of y. The inside for y is -1 to 1. The dx 1 to 2. Right, let's say that integral b. Right, and I mentioned before, limits are constant, function separable, so just put all the x together. And all the y together. Right. By the way, I did say this one is a bit tricky. We can integrate 1 over x, which is ln of absolute value of x. That's easy. But once again, if this one without the limit, I don't think anybody, I'm not sure, but that integral, we cannot do it. If it is just sine y cubed, we cannot integrate y cubed. Alright, so what can we do here? First of all, let's just look at the calculator. What if we put in the calculator? This is not sine y cubed, this is sine of something cubed. Like that. So that's 0. And we set y 0. Right. Now to answer that question, ask you, this is one section in calculus 1. It's about the symmetry. We have the symmetric limits here, right? From negative to positive. So is the function here even or odd? Because if this is odd, the function is odd, that area with one above, one below, those cancel out. So the total, the net area will be 0. If it is an even function, this area are the same. So we're going to double. Right. So is that function odd or even? So I just want to write this little note here. Then odd function is where we have f of negative x equal to negative f of x. And they'll say sine is an odd function, and yes, sine is an odd function. So this is an odd function. But we have to do a little more than just say sine is an odd function. Right, just take a look at this. Right. Let's do sine of, if we put negative into it, so, negative cube it's going to be negative cube. And sine is an odd function, so we can take it outside. So sine of negative is equal to negative of that. So this one is odd. If the function is odd and the limit is symmetric, one positive, one negative, that integral is equal to 0. So you don't even need to integrate this because the second integral is equal to 0. So we have 0. Right, just make sure that we want to see that if the function is odd or even, I just consider the graph sine of x cubed, right? Right, so that is the graph. Right, and I can see obviously this is symmetric with respect to the origin, so this is odd. But then actually it's not very obviously to see, so kind of difficult to see that if this one symmetric on the origin or not. So I can just do this. Why don't I will graph negative y, I'm going to enter y1 here, variable y1, and I can just graph that. Be opposite of that. If the graph are the same, if the graph of these two are the same, the function is odd. If I don't have the negative here, if I don't have this negative, the function, and they are the same, they will be even. Right, let's look at the graph. That's nice to know, but what if the second function graph exactly like the first one? Won't be able to see that, right? So I recommend you do this. Go in front of the y2, hit 1, 2, 3, 4. You see this pattern, a dash and a circle. And now look at the graph. It will graph the first function. So this is the function. And I will graph the opposite of negative x function. Okay, you see. It graph the second function by the little dot. The little dot just trace on the first function. So these two functions are identical because the second function just trace exactly on the first function. Right. So put in the function, and then if we don't have the negative and the graph are the same, they are even. If there's negative and the graph are the same, they are odd. By the way, it just show by the graph. Actually show that it is an odd function. That's what we need to show. Right. So not that bad, right? Compared to the last problem. Right. Now, average values of function is just an application. So say the average values of the function is equal to 1 over the area and then the double integral. So let's find the average values of this function. Later on we'll talk about this, but for now it's just an application. Where the average values of the function is 1 over the area. Worry about that. By the way, x go from 0 to 2. Y go from 0 to 2. So we talk about this square. So sometimes it is better to just draw a picture instead of describe what you have there. So double integral the function 2 minus x minus y. And let's say we put dy in the inside. I said usually if I have a choice, all things being equal, I prefer to put y in the inside, because after that we have x on the outside, will be like the normal integral. Right. The area of this one, 2 by 2, so it's 4. integral this with respect to y. X is a constant, so 2 is a constant as well, so we have 2y minus xy minus y squared over 2. Y go from 0 to 2. Right, I'm substituting 2 in for x, 2 in for y. 2 in for y, 2 in for y, and 2 in for y. And then subtract 0 in for y, and for y, and 0 for y. So this will have 4 minus 2x minus 4. Sorry. 2. And 0, 0, 0. So that's all gone. Yeah. 1/4, 0 to 2. And 4 minus 2, so that's 2 minus 2x. This is actually simple enough. I'm just going to do this by hand. Will be 2x. Integral of x is x squared over 2. Go from 0 to 2. Cancel out the 2. 1/4. 2x minus x squared. From 0 to 2. Right. Put 2 in for x. 2 in for x. Subtract 0 in for x. 0 in for x. That one gone. And 1/4. 4 minus 4, so actually that's just 0. So 0. Yeah, so the average values of the function is 0. So you see, actually we have the graph. I'm not sure you see this or not. The function, the 2 minus x minus y, this is the kind of the diagonal plane. So that is the function. And we see half of it is above the x-axis, half of that is above the xy plane, and half of it is below. So the average, if you have half above, half below, that cancel out will be 0. So that's why the average values should be 0, and in this we have 0. Right. So that is this first section of the double integral. So bottom line is, the most important rule in this is whether we do dx, dy, or dy, dx, the inside integral, we treat the other variable as a constant. If we do dy dx, the inside, with respect to dy, with respect to y, x is a constant, and vice versa. So that's the most important things when we do the integral. Just treat the other variable as a constant. And then on the outside, we just have one variable, right? And we just integrate that. So that should be, that should not be a problem. Right, so that's what we have. Right, in the next section we'll study about a more complicated case when the limits are not constant. But for now, the limits are constant. Because they are constant, we have the constant on the x-axis, constant on the y-axis. So that's why we call this is the rectangular regions. Yeah, like 0 to 2, 0 to 2, 2 by 2. In this case. Anyway, I'll stop this section here, and we continue when we have more complicated problems in double integral. As always, thank you for watching.